Hi everybody, in this video I'm going to go over study section 4.3.3, which is balancing organic equations. The first thing we need to know about balancing organic equations is what an organic molecule is. So an organic molecule is any molecule that is carbon-based. That means that it contains carbon as the main element. So all organic molecules are carbon-based. Okay? And something interesting about organic molecules is that all living things are made up of organic molecules. So people, animals, plants, they are all primarily made up of organic molecules. We contain a lot of carbon. All living things are made up of organic molecules. Okay, and the reason why this organic molecule is so special and so important and it happens is because carbon has 4 very stable bonds. So if we drew a Lewis structure of carbon, we know that there's 4 valence electrons. That means it can make 4 very stable covalent bonds. And as a result of that, there's lots and lots of molecules that are carbon-based. And it's special because carbon forms 4 stable covalent bonds. Okay? So that's what organic molecules are. The next thing we need to be able to do is represent organic molecules. All right, so there's 3 ways of doing that. The first way is called a ball and stick model. And this is what we've seen in the classroom, right? So we've made these ball and stick models. They're physical models, and they show the geometry of our molecule. So in this, the blue is representing our carbon and our red is representing our hydrogen. Now, I can't draw in 3 dimensions. A lot of these are computer renderings or physical models, but they should show the 3D structure. That's why they're useful. Okay? Next is something called a structural model. And this is like a Lewis structure. So we've seen these before. All these models are representing the same organic molecule that has 3 carbons and 8 hydrogens. Okay, so the structural model, the reason why it's useful is it shows the atoms, all of the atoms, and the bonds. And the last model is the stick model. Now, the stick model is simpler, but a little more complicated to understand. So, the stick model, it is a shortcut. It's useful because it's a shortcut, okay? But it doesn't show any of the atoms written out. But we know that there is a carbon at every corner, or at the end of a line. Okay, and the hydrogens are not shown. Okay, so we would know looking at the stick model that there's a carbon here, and a carbon here, the end of each line. Okay, so what we need to know is if I gave you a model, you should be able to tell me, is it ball and stick, is it structural, or is it stick? And if I gave you a stick model, I would like you to be able to tell me how many carbons there are. So let's do an example of that. Let's say I have this. Okay. Now, we're trying to figure out how many carbons are here. So we need to count the corners. 1, 2, 3, 4, 5, 6, 7, 8, 9. This has 9 carbons. Now we can do the same thing. There are some molecules that are cyclical. It means they're sort of in the shape of a circle. And we would do the same thing. At each corner, we count the carbon. 1, 2, 3, 4, 5, 6. So this would have 6 carbons. Okay? So that's everything we need to know about representing organic molecules. So now let's move on to combustion reactions. Combustion reactions are the most common reactions using hydrocarbons, and it occurs when you burn a hydrocarbon. It also occurs in cellular respiration. Okay, if you remember from biology, cellular respiration is when you take in a hydrocarbon like glucose, and in every cell of your body, it then converts that to energy. So the general form of a hydrocarbon reaction is that you have a hydrocarbon plus oxygen gives you carbon dioxide and water. Okay, this is a combustion reaction. I'm sorry, not hydrocarbon. So what a hydrocarbon is it's just any compound that contains just carbon and hydrogen. Okay, and it sort of seems strange that there would be water in this, okay, but water is actually in the form of water vapor. So like if you turn on your stove, that is a combustion reaction. You are burning a hydrocarbon, you're burning methane. And water is produced in the form of water vapor. Okay, it's a gas. And also I want to add here is that heat is always produced in a combustion reaction. So we can see here that our reactants are always a hydrocarbon and oxygen, and our products are always carbon dioxide, water, and heat. Okay, so how do we balance this? There's a certain set of steps. Balance combustion reactions. So when we're doing this, the first thing we want to do is balance carbon. The second is we balance hydrogen. The third is we balance oxygen. And our last step is you multiply coefficients, those are the numbers in front, by 2. And you only have to do this if you end up with a fraction. So let's do an example so I can show you what I mean by that. Okay, so we have our hydrocarbon, C2H6, plus oxygen gives us carbon dioxide and water. So like I've done last time, I'm going to make a list of the atoms I have. So I have 2 carbons on the left, 1 on the right, 6 hydrogens on the left, 2 on the right, 2 oxygens on the left, and 2 plus 1 is 3 oxygens on the right. So let's start by balancing our carbon. So we have 2 on the left, we need 2 on the right, we only have 1, so we're going to multiply it by 2. That's going to change our carbon to 2, so that will be balanced. But now it's also going to change that oxygen. So we have 2 times 2 is 4 oxygens plus 1 more from the water. So this gives us 5 oxygens. We're not going to worry about that right now because our second step is to balance hydrogen. So we have 6 on the left and 2 on the right. So what times 2 gives you 6? It's going to be 3. So 3 times 2 is 6, and our hydrogen is now balanced. However, that does change our oxygen as well. So now we have 2 times 2 is 4, plus 3 is 7 oxygens. Okay? So now we need to balance the oxygen here. We have 2, and we need to get 7. So 2 times, that's not going to be a whole number, right? 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8. So it's going to be 3.5. 3.5 times 2 is 7. Okay, so now this is balanced, but now we have a fraction. Okay, and we don't want to have a fraction in our final answer. So what we're going to do is we're going to multiply everything by 2. So this would have been a 1. We're going to multiply it by 2. Okay, and then we'll rewrite this as 2C2H6 plus 3.5 times 2 is 7O2 yields 2 times 2 is 4CO2 plus 3 times 2 is 6 water. And that would be our final answer. Okay, so we balanced our carbon, then our hydrogen, then our oxygen, and then if we have a fraction, we have to multiply all of the coefficients by 2. Let's do one more example here. Let's say we have C5H12 plus oxygen yields carbon dioxide plus water. And again, I'm going to make my list. 5 carbon on one side, 1 on the other, 12 and 2, 2 and 2 plus 1 is 3. All right, here we go. Balance our carbon first. So 5 on that side, we need to put 5 here. This becomes 5. That does change our oxygen. So now we have 5 times 2 is 10, plus 1 is 11 oxygen. All right, now let's do our hydrogen. We have 12 on the left, 2 on the right, so we have to multiply by 6. 6 times 2 is 12, and our carbon is done. But now it changes our oxygen. So we have 5 times 2 is 10, plus 6 is 16 oxygen, and 2 on the left. Now, 2 times what gives you 16? That's going to be an 8. That is a whole number. So now we have 16, and we are balanced. Now, we can see that all of these are whole numbers. 1, 8, 5, and 6 are whole numbers, so we do not need to do that last step of multiplying everything by 2. You would only need to do that if you got a fraction or a decimal. Okay? So, this is everything that we need to know about organic equations. We need to understand what an organic molecule is, how to represent it, how to determine how many carbons there are. We need to know what a combustion reaction is and how to balance it. Okay? Hopefully that was helpful. Thank you very much.